Okay guys, velocity and acceleration for motion along a curve, which is just going to be another name for vector calculus, where we're doing some velocity, some acceleration, some speeds, some collisions, and lots of fun. Okay, so let's get into it. Velocity. Now this is a recap, except for the last bit. Velocity has previously been defined as the rate of change of position, displacement. Yes, we know that. It follows that this velocity vector function can be given by this. Yeah, it's the derivative, or the little dot above denotes the derivative of the position vector. Now this might be a bit new for you. You really need to think about this very closely. The velocity vector, not the position vector, gives the direction of motion at a time t, because it basically gives you the proportions of x and y moved in every interval of time. Therefore, the orientation of the distance travelled per unit time gets you the direction of the motion over that interval of time. So please remember, it's the velocity vector that gives the direction of motion, nothing else. Okay, that's really important, and we'll need that information in a moment. Acceleration, yes, that's same old. It's defined as the rate of change of velocity. Therefore, it follows that the acceleration vector is the second derivative of the position vector, or the first derivative of the velocity vector function. All right. Speed is just the magnitude of the velocity, right? The magnitude of the velocity. This is the velocity, and its magnitude puts the modular signs around the outside of it. All right. Now let's go and do some examples. We've got an object here, and that is its position vector function. We've got to find the velocity vector, the acceleration vector, and the speed. No problem. Okay, here's the position vector. Derive that, do the derivative of that to get the velocity vector. See if you agree. Do you? Yes. Good. There, Mr. Box, thank you. And part B, the acceleration vector, just do the derivative of what's in the box above. This component doesn't change because it's just e to the t. This one does because it's got some chain rule in it. Okay, yes, there it is. That's the acceleration vector. Now we've got to do the speed. Speed is just the magnitude of the velocity vector. So this is the x component, that's the y component of the velocity vector function. So if we do Pythagoras' theorem and say it's the x component squared plus the y component squared, square root of all that, we get the speed. Now that can probably be simplified a little bit, but as far as I'm concerned, that's an adequate answer. But I think I did fiddle with it a little bit. I multiplied the bracket out, and then I thought, oh yeah, okay, I can take e to the 2t out of both terms, and the e to the 2t taken out of the square root, so I'll just get us e to the t outside, and that gets you that answer. So that's our speed. There's our speed, guys, and thank you again, Mr. Box. Alright, now over the page we go, and this is a collision question. Woo-oo, this is a collision question. So let's just have a look at it. This is particle A, position vector function of. This is particle B, position vector function of. We have to prove they collide while they're travelling at the same speed. Alright, there's a lot in that. Alright, well let's do the collide first. And okay, they're travelling at the same speed. That's pretty easy. I can see how to do that. And the right angles to each other. Now that bit there, the right angles to each other means you need the direction of travel, and to prove that that is at right angles to each other. Now the direction of travel, guys, is obtained from the velocity vector, right? No other vector than the velocity vector, not the position vector, not the acceleration vector, not any other vector but the velocity vector. So let's do that. Alright, now here's our collision bit. Now, there's particle A and there's particle B. Now, for collision, we need the x components to be the same. This has got to be the same as that. Okay, and that will happen at certain times, and the y position has to be the same for particle A and particle B, and that all has to happen. The x's have to be the same, and the y's have to be the same at the same one single time. Okay, so that's how we're going to approach that, and we're going to write that mathematically in that way. There's your x's are the same, there's your y's are the same, and I've left t as the variable because t is going to be the same variable in both of those equations 1 and 2. So now I'm looking at equation 1. I'm reorganising it, so I get that. That's a bit troublesome because that's a cubic and we probably have to guess and check to work out some roots of that cubic equation. Yes, alright, 1a. Now, equation 2 is a bit easier because it's a quadratic. I've reorganised it, and that's 2a. Now, we've got to solve both of those, and we've got to work out the solutions that are common to both of them, right, in terms of time. So if you've got solving equation 2, the quadratic is the easier one to go for first. That easily factorises and gives us solutions t is 1 or t is 2. Now that means that when t is 1 and when t is 2, that means that the x components, no, it's not the x, it's the y components, this and this will be the same as this at t is 1 and at t is 2 for both of those particles. Alright, now let's get into 1 now. If you guess and check and fiddle with that and you plug t is 2 into here, you get a root, okay? You get a root. So basically we've struck gold. We know that t is 2 is a root of that thing. So therefore I've re-expressed it in the terms of this after doing some fiddling. I'm assuming by now that you know how to do that. How to long divide t minus 2 into this to get that as the quadratic-y bit, quadratic-y factor of this expression here. And therefore I've gone ahead and I've tried to fiddle with that a bit more, and I've got to here and I've thought, oh yeah, well, look, having a look at the solution to equation 2, which was the y components of A and B, I got t is 1 and t is 2, right? Well, I've got t is 2 up here for the x components, but this is no way known this is going to result in some whole number solution, because that's going to be, that thing there is the square root of 21 over 2 all squared, so therefore, you know, forget it. We're not going to get any whole number solutions. So therefore, I think really all that can be in common is in terms of the times, in common when both the x components are at the same place and the y components are the same place, will be t equals 2. T equals 2. So therefore, I don't need to go any further. T is 2 is a solution to both equations, 1 and 2. So the x's are the same and the y's are the same at t equals 2. This looks like the one we're after, guys. Okay, so armed with that information, we can now plug t equals 2 into the things that we've got. But we first of all need to know. We need to know that what are we doing? We're proving that they collide while they're travelling at the same speed. So we have to work out the speed, and yes, and we have to prove that they're at right angles to each other using the velocity vectors. Alright, well that's alright. We're going to plug t is 2 into these equations now. There they are. I've worked out the velocity vectors. I've done the derivative of this, and I've done the derivative of that one, and there's where I'm at, right? Now, I think we better plug in the values for t is 2. Okay, therefore that's what A is doing when t is 2 in terms of its velocity, and that's what B is doing when t is 2 in terms of its velocity. Alright, now the speed, let's prove that the speeds are the same. That's what we've got to do from up here. That's pretty easy. You can see that, can't you? Okay, you can see that sticking out a mile. So the speed of A at 2 seconds is the magnitude of its velocity, which is that, which will be 5. Yes, and the speed of B will be exactly the same, because you can see there that also comes to 5. So we've proved that they collide. We've proved they collide while they're travelling at the same speed. All right, but we have not proved that they collide at right angles to each other yet. All right, we will do that in a moment. Now that's where we got to. So let's go. Yes, we've proved that. Now, okay, we've got to do the dotting of the velocity vectors. The velocity vectors at t equals 2 seconds, and if it comes out to be 0, then we've proved that they are at right angles to each other as well, because neither of these are 0 vectors in and of themselves. That should be RB at 2, okay? There it goes, and you get that, and you get that, and therefore look at that. Oh, look at that. That comes to there. That comes to that, and that comes to 0, which is exactly what we want. So I think we've just about done it now, guys, haven't we? Haven't we? Yes, so therefore they do collide at right angles to each other aka the dot product comes out to be 0, and they do collide at the same time, which we proved. T was 2, and at the same speed as well from over here, yeah, from earlier in the question. So that's it. We've done everything they asked for, guys, and we feel mighty fine, don't we? We do. Now, okay, what's this one? Let's have a look, study it, and see what we're doing here. Well, I think this looks fairly straightforward. Let's go for it and see what we find out. We've got A, okay? We're going to find the velocity. Well, that's a nice, easy way to start off, isn't it? Eases us into the question. So let's take the derivative of the position vector. We get that. That's our velocity vector. Have a look. See if you agree. Do you agree? Good. Well, I agree too. So we're all in unanimous agreement. Now, the speed of the particle. Now, that's going to be a bit of an interesting one. The speed. That's the magnitude of the velocity. So let's go for that. That's pretty interesting. So that's this beastie squared, the x component squared, plus the y component squared, plus the z component squared. We get to that. Now, that's pretty interesting. If you have a look at this, they're asking us for maximum speed and minimum speed, which is a bit troublesome. Unless we do a few little tricks here. If this was a tech-free question, which let's assume it is, you've got to find a way of navigating your way through all this stuff, the mire of the trigonometric jungle here. But I think what we can do is a little trick which is devilishly cunning. Now you watch this, have a look. So what have I done? What have I done there? Well, ladies and gentlemen, I thought, he looks a bit lonely here. Let's just borrow 4 of these 16 cos squared 2t's and match them up here. Here, look, 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 look. Isn't this great? So now I can call that equal to just 4. 4. Yes, because sine squared plus cos squared equals 1. So 4 of them equals 4. And I've been devilishly cunning, and I've reduced this down to a single trig term in here, together with just 8. Okay? So that's pretty nice, and that gets us a lot more simplicity with which we can then tackle this kind of stuff and that kind of stuff. Yeah. Otherwise, I think it's just a little bit impossible, unless you're a genius, and I'm not. So here's part C for you and me. That's part B done. Thank you, Mr. Box. Now, the maximum speed, of course, ladies and gentlemen, this is a cos squared thingy. So it can be never can be negative, but the maximum speed would occur when this thing equaled its maximum value, which would be 1 times 12. It gets you 12 plus 8, which would be root 20, which would be 2 root 5. Okay, that's got to be the maximum speed. Isn't that great? Don't you love it? I certainly do. And now, the minimum speed. Okay, the minimum speed. Now, have a look at this. Come on, you've got to get your thinking cap on here. How would we do that? Well, it's no use picking the minimum value of cos 2t because that's minus 1, and we're just going to square that. So really, to get the minimum value of this term here, you've really got to choose when this thing here, when cos 2t equals 0, okay? 0. Because it's only ever going to be 0 or positive. That's the point I'm trying to make. So therefore, when this thing's 0, 12 of them equals 0, and therefore you're just going to get a minimum of root 8. Yes? Yes, yes, 2 root 2. I know, it's pretty marvellous, you know, and these questions are so elegant and so beautifully put together. If you can see through the camouflage and just do a little bit of pea and thimble, a bit of smoke and mirrors, you can always get to the end, and the answer is never very far away. That's my motto, guys. I'm always harping on that. The answer is never very far away, so just look for it. You'll find it. Alright, what's this? Position of a projectile at time t is given by that thing. We've got a projectile now. Alright, that's the path. That's the position vector of the projectile, where t is greater than or equal to 0, looks like time, and I is a unit vector horizontal, yes, and j is a unit vector vertically up, and we don't have a k, which is very nice. We don't want 3 dimensions, we're just having 2 dimensions. Thank you. So therefore the projectile is fired from a point on the ground. Find the time taken to reach the ground again. Yes, alright, we'll go for that. I think that's very, very, very simple. You can see that this is a parabola. I really like that. That's a parabola, the vertical component of the motion. So that works in our favour later on in the question. The time taken to reach the ground. Well, you've got to interpret that. You've got to interpret that. The time taken to reach the ground, basically, that means that the j component of the position vector function will equal 0. Alright? So you basically set it equal to 0. That's the vertical component there, the y component. Alright? So then you just solve it for t, and it's very easy to solve for t. It's a quadratic expression, so therefore t is going to be 0 or t is going to be 100. Okay? Now, the t is 0 is the point at which it was projected in the first place, right? Projected, okay? Now, b, what have we got here? B for you and me. The speed of at which the projectile hits the ground. All right, well, okay, let's do that. So we know that the velocity vector will be that. I've taken the derivative of this beastie here. Yeah, there and there. All right? Now, what we've got to do is get the speed when it reaches the ground again. That is when t is 100. So therefore, that's the velocity when t equals 100. Now let's just convert that into speed by finding its magnitude. That's what you get there, and its magnitude would be that. Okay, and that's an easier way to do it. Rather than getting telephone numbers, just factorise out the 100 out of each of those expressions, or the 100 squared out of each of those terms, and you'll get that, which means you're going to get that. Okay, so that is the speed at which the projectile hits the ground. It's pretty fast, isn't it? So there we go. So now, part C, the maximum height of the projectile. Now that's an interesting one. What about you give that a little bit of thought, pause the video and see how you think you might do that. Okay, how did you go? Alright, well the maximum height occurs because this is a quadratic function, right? It's a quadratic function here. So you know you can treat it like a quadratic function. So we know that it starts at t is 0 and it's going up and then it comes down again. Well, basically the maximum height's going to occur in the middle, because quadratic functions are symmetrical about their turning points. Okay, so it's going to reach its maximum height when t is 50. So therefore, that's really easy to work out now. So therefore, the j component when t is 50 of this beastie here is going to be 500 times 50 minus 5 times 50 squared, which gets us this, which gets us that. 12,500. Is this in meters, or is it, or what is it? It doesn't say, does it? No. Alright. So that's 12,500 units, alright? Now we're nearly there now, guys. We've only got D to go. The initial speed of the projectile, okay? The initial speed. So therefore, there's our velocity vector, and we've got to plug t is 0 into that, and we get that, and therefore it's going to be, oh yes, look, that's very interesting. It gives us the same speed as we got when it actually hit the ground at t was 100 seconds. So therefore, yeah, same thing. That's what we got before, but in this case it would be 400i going up plus 500j, yeah? But it comes down, whatever goes up must come down. If it does it in a quadratic fashion, that'll be the j component on the way down, yes? There it goes. Do you like it? I think it's pretty marvellous. The initial speed is 100 root 41. Alright? Now, I think that's the end. Yes, and that's the end. Hello, Mr. Star. You'll go far, huzzah. And in fact, it's time for celebration because it's the end not only of this video, but it's the end of the entire Specialist Maths course. So I hope you enjoyed being with me. It's been tremendous fun doing it for you. I hope you've got a lot out of it, and we'll see you anon, no doubt in the future sometime, someplace, and all the best to you.